All right, so we add one more wheel. We talk about 4 wheels. 2 wheels in the front are steering, and also they have traction. The back ones are with fixed wheels, as with a tricycle. Right, so this is basically like a car. Anyone drives car here? All right, so when you steer, are both wheels steering the same, different amounts? Different amounts. Right, we don't have the same steering angle for both. Why is that?
Because the outside wheel moves faster than the inside one.
When we turn, okay. Yes, that's kind of the same thing as the condition that we have, that I said earlier, that the instantaneous center of rotation have to be basically on the axis of rotation of both wheels, of all the wheels, right? So if we want all the wheels to intersect at a single point, then when I'm steering, the left and the right wheel have to turn by different amounts, slightly different amounts. So this is what we call the Ackermann drive. And it's illustrated here. Right? Because I have a bigger distance here for the right wheel, it has to turn basically less when I'm steering to the left, and so on. It's the same thing as what you're saying. I have a different radius basically from the instantaneous center of rotation, so in order to have the same angular velocity, then the linear velocities have to be different. Right? So it's the same kind of constraint. All right. And the condition is that this alpha is bigger than beta when I'm turning left, and the other way around when I'm turning right. And obviously they have to be the same when I'm going to go straight, and they have to be equal to 0. Right? How do I calculate the instantaneous center of rotation based on this? The question is more like, how do I calculate the relation between alpha and beta based on the instantaneous center of rotation? And I can do this purely based on trigonometry. I can calculate these angles alpha and beta from these triangles and these dimensions, the distance between the wheels and the distance from the rear wheels and the front wheels. I calculate based on cotangents, or I can do the inverse and its tangent. What do I have here? I have these triangles. Let's write them down. So I have this one, or let's do it the same color as on the, and then I have blue here. So I have this one and this one, and then white. I don't know, whatever, I put the wheel somewhere. Okay, and I have this distance D. I have this length L. And I have this length, which is the instantaneous center of rotation. Right, and I have this angle. Let's make this bigger. Alpha and beta. Okay, so what do I have here? I have R minus L over 2, so it's basically this distance. Let's use yellow. Okay, and then this distance D. Okay, this is the cotangent of alpha, alpha being this angle. Of course, I could have taken D over R and it would have been the tangent. I don't know why I took the cotangent. Right, and then again this angle is beta, so it will be, let's use pink, that I never used. This is, sorry, until here, it's R plus L over 2, L over 2 being the half of this, right? It's L over 2, L over 2, right, and D. Again D, and I can calculate beta. Right, so if I know R, the center of rotation, and I know the dimension of the robot, L and D, I can calculate veta in alpha. All right? If I take the difference between the two cotangents, I get a ratio between the width and the length of the robot. Okay, what happens when alpha and beta is 0? What's the radius? When alpha is 0, cotangent of 0,
Infinity.
it has to be infinity, yeah. That means that R is at infinity. Makes sense. Now, as you said, Andrei, it's not just the angle that is different, it's also the linear, the angular velocities of the wheels. What's the condition there? So here I will have some wheel velocity left and right. I will have the same angular velocity for both wheels, but I have different radiuses, this red and blue line. Right, so how do I calculate UL and UR?
UL is the angular time.
So it will be again UL angular times the red line, I don't know, HL, hypotenuse L. UR will be omega HR, and HL is how much?
R minus
L over 2 square plus D square, square root, that's one way, or it can be, I don't know, the sinus of D, sinus alpha D, can do it whatever way we want. Okay. It was has is has times sinus is D, so it's D over sinus of alpha. This will be omega D sinus beta. Okay, and if I take the omega left, omega R, this will be over R over R, so this will be over R. Okay, so I take the wheel velocities. So the wheel velocities will be different as well for a certain steering. Okay. How do I calculate forward inverse kinematics? We basically consider a virtual third wheel in the middle, which should also respect these geometric constraints. Okay, so I put another wheel here, making sure that it's still oriented in a way so that it intersects this horizontal line at the same location. And I calculate this angle gamma, virtual angle gamma, which I can do again from trigonometry. Gamma will be slightly bigger or slightly bigger than alpha or slightly smaller than beta, or it depends whether I'm turning left or right, but it will be between the two. And then if I consider this virtual third wheel gamma, I use the modeling from the tricycle, right? So I'm not going to recalculate things. We could recalculate based on the two wheels, but we'll end up with the same result as with a tricycle, because it's kind of the same model in the end. Okay? Good. There are two different types of four-wheel robots. We have this one that is called the Ackermann drive, where I have two wheels rotating and steering, different angles. We also have these robots that we call them the skid steer drive. So we have four individual driven wheels, but they're not steering. All right? The left and right wheels might be coupled together. So I might have the left wheels rotating with the same velocity and the right wheels rotating with the same velocity. or they can be also all independent, but the idea is that I don't have any steering, right? And the way we are steering this robot is by changing again the individual velocities. Now, what's the issue with this design? Can you see the flow?
Something with the center of rotation, right?
Yeah, where would be the center of rotation for these robots?
Always in.
Yep, exactly, because I have basically the two, we said that the center of rotation will always be at on top of the axis of rotation of the wheels, of all the wheels. It will be where they intersect, but these four wheels have like parallel axis of rotation, so they will never intersect. All right, so it will always be at infinity. That's if I don't have any slipping. The reality is that if I move the wheels with different velocities, I will start having slipping, right? Because imagine even if I have the wheels not steering, if I move the left faster than the right, I'm not going to go straight. That would be basically instantaneous center of rotation at infinity, going straight, right? But this is not going to happen. I will start having what we call skidding. That's why it's called skid steer, or slipping, right? So I will have like slipping. So typically we use the same kind of modeling as differential drives because the left and right wheels move independently. But in reality, I always lose the assumption of no slipping unless I'm moving straight ahead. So then I have this issue. Right. I will have some kind of trajectory based on the differential drive that I'm trying to execute. Right, so this is what I'm commanding, let's say, but the actual thing will be something else. And the problem is that I cannot always predict what this else thing will be. Because I don't know exactly all the dynamics for slipping based on, I don't know, the wheels and the ground and the interaction between them and, I don't know, center of masses and all this, the dynamics and everything, right? What we're trying to do is kind of estimate the slipping, and based on a feedback loop, we're trying to correct for that, right? So, as I said, we assume a differential drive model, which is what we saw earlier, but here we don't consider any lateral movement, right? We just move straight or rotate. In order to introduce this uncertainty for the slipping, we also add some lateral movement, which we call slip. Right, so I have basically the forward velocity, I have the sideways velocity, and then the angular velocity. In an ideal scenario, I consider this to be 0. That's why I have 2 zeros here. So I always have slipping 0, right? But then I basically add some disturbances. So I'm trying to model this slipping with some coefficients for disturbance. So I'm trying to write this basically kind of like in state space, where I add some unknown disturbances. Some ways to model these disturbances, I can assume them to be proportional to the linear and angular velocities of the robot. So these three are the three disturbances in the three directions that I had here. Right, so basically this is like a linear combination of some factors, A of this, A11, A21, A31. Basically I can write in a matrix form. And yeah, I'm trying to estimate them by making models. These variables will depend, as I said, on the interaction between tires and the ground. So it depends on what kind of ground I have. Is it slippery? Is it gravel? Is it, I don't know, asphalt? Is it what kind of ground I have? It will depend on temperature. It will depend on different physical quantities, and you know, it's usually very difficult to predict. And even if we have like something that works on a certain environment, the moment the environment changes, then I'm lost. I don't know what these variables contain. So when we cannot rely on it, we have to have like a closed loop system where we are basically estimating how much slipping happened, and I'm trying to correct based on that. That's the idea. Probably you heard about IMUs, inertial measurement units, where there are sensors which they give me some sense about velocities and orientations, and by using that we can, close the loop and basically correct for that. I'm not going too much into details here, that's like a whole big chapter. Depends on, if you go to masters, depends on which masters you go, you will learn more about these kind of techniques. What I would like to do before we finish is to talk about the dynamic model, because that's things that we have already developed and for robot arms and drones, so then we can do it also for the mobile robot, and we see what's different here. So if we want to have a dynamic model, which would be useful also for the control aspect that we just saw now, how do we proceed? Any idea based on what we saw? What would be your approach? What is a dynamic model? It's the model that gives me the equations of motion for the robot. So basically connecting the input that we give to the robot to some output, right? Input would be some forces and torques, and output would be accelerations over time. How did we do this for robot arms and the drone?
So the Lagrangian system in the other.
Right. So we have the Lagrangian, and for the Lagrangian, if you remember, we had to choose these generalized coordinates, which would be describing the state of the robot and would be basically, where the input for our robot would happen. For the robot arm, it was the joint coordinates, because that's where the input was, the torques at the joints. For the drone was XYZ on the drone model, on the drone frame, and the torques generated by the rotors. What would it be here?
The angular velocity of the wheels.
All right. It would be basically its positions and velocities. The coordinates would be the positions of the wheels, right? And then we will end up using also the velocities, so the derivatives of the states of the coordinates. That would be the states. It would be, the coordinates would be the position of the left and the right wheel, and the states would be the coordinates plus the derivatives of the states, so it would be the velocities. All right, but we take it from the positions. Right, so F, phi L and phi R is the angle of the left and the right wheel. Okay? So if we want to derive the Lagrangian based on these generalized coordinates, what was the Lagrangian? How did we define it? T minus V, kinetic minus potential energy. All right. And the kinetic energy we split into linear and angular. All right. And for the robot arm, we split it in the links of the robot, and we calculate the linear and angular velocity of each link. Here, what part should we consider? Well, for the drone, it was just one object for the simple model. All right, here, what would be? What?
Everything already to like the angular and linear velocity.
Yes, we know, right? So we're talking about the whole kinetic energy of the whole robot, or do we break it down into parts?
No, whole robot.
Whole robot, all right. Depends on the detail of the model that we want. In the example I have, I basically calculate the whole robot, and then I take separately the angular kinetic energy of the wheels, because they basically can move, in different velocities. So I have differences there. We can also take the linear and angular velocity of each part, so the frame of the robot, the body of the robot, and the wheels, but I think we will end up with the same result if we take the linear velocity of the wheels separately or as a whole. Right. So here we will have the linear velocity of the base, angular velocity of the base, and the kinetic energy, not velocity, sorry, and the angular velocity of the wheels, wheel 1 left and right. All right. Because they will rotate in slightly different ways. So the wheels rotate both around the theta angle, but also around their own axis. So we have 2 rotations there. All right. So let's see what is the linear velocity. And yeah, this Lagrangian has to be a function of what? Phi left, phi right, and omega left, omega right. The 2 coordinates and the derivatives. Right, so let's start. What would be the linear kinetic energy of the body? How do I calculate that?
A mass, which is
Right, 1 over 2 a mass.
velocity squared
What velocity?
of the body, which we have.
Yep, so that would be u squared, right? And that's it. But this has to be a function of phi, or omega, omega. Right now it's not.
But we can break down u to be.
We can break down u and write it as a function of wheel velocities. We already did that. That's the forward part of the forward kinematics. Right? You remember?
Yes. So it was 1 over 2, no?
1 over L, length of the...
1 over L.
Yeah, it will be 1 over 2 mass 1 over L, this part, all right? I think so, right?
And the sum of the 2 divided by 2.
They were subtracted over the sum, I think.
They were the average of the 2. Sorry. Square. And this was times r. Times r, which is the wheel radius. Okay, and now we have this as a function of omega left and omega right. Right? Similarly, the angular velocity of the body, the angular kinetic energy of the body will be 1 over 2, some inertia. I call this YZZ, which is the inertia. So I will have to calculate the moment of inertia for the body. You remember, but since I only have 1 rotation, I would take the element that corresponds to that rotation. If I really want to write it properly, I would have to take angular velocity as a vector, which would be 0, 0, 1. I would take the whole moment of inertia, now 0, 0, omega, because I have only rotation on the z-axis, and I will end up just taking the YZZ element from here times omega squared. So since we are familiar with this, I'm skipping this and I'm writing it as a scalar, not as vectors and matrices. So it will be this inertia for the rotation around z times the angular velocity squared, right? Which again I can write as a function of wheel velocities. Okay? Oops. So I'm just giving it here. Yeah, which would be basically this part. It's the body linear velocity, kinetic energy, and this part is the body angular kinetic energy. I have it in different way here, but yeah. Right. What is the angular kinetic energy of the wheels? Now I don't have any omega rotation, omega capital omega rotation. I have 1 over 2, the inertia of the wheel, and The velocity of the wheel.
And my question is, can't we just skip those if we assume that the mass of the body is significantly larger than the mass of the wheel?
Yes, you can simplify. I mean, we're engineers. We do that all the time. But yeah, it depends on the magnitude and the relevance.
Okay.
If the wheels are too small compared to the body, you can ignore it. Or also if the velocities are too small or the inertia of the wheels is too low, you can ignore it. But it's not that complicated to also include it, right? So this would be for the left wheel. And if we assume it has the same moments of inertia, both wheels, because they have the same radius, it makes sense that it's the same. I can just calculate for the two wheels. All right, and that's what we see there. So here I wrote the whole kinetic energy. So here I have, yeah, this form is what we write. Right, and if we expand this, I take the u as a function of omega r and omega left, I get this part. And if I expand the squares, I get something like this. This is just expanding the binomials, right? And if I refactor and I take, basically, I factor out omega r square and omega l square and 2 omega r omega l, I get it in this form. Okay, so this is the total kinetic energy of the system, considering what we consider. What about the potential energy?
What stays on the ground?
Then
It's small.
You can consider it 0.
we can consider it 0, we can consider it some value, but the point is it will be constant. Depends on the reference that we get for calculating the height, right? Right, it doesn't matter the value. We see that for the potential energy, only the derivative of the potential matters. So if it's 0 or constant or whatever, the derivative will be 0. So we'll see that it doesn't affect us at all, right? This is again the assumption that the robot moves on a plane. If we start having like uphills, downhills, whatever, then we can also consider differences in the potential, but that's not a function of, I mean, it is a little bit of a pain to convert it to a function of wheel positions, because it will depend on the terrain, right? So then we have to find a way to, I don't know, for a certain trajectory, calculate, okay, how does the potential change over the trajectory or something like this. All right, now that I have the Lagrangian, what? With the Lagrangian is basically this minus a constant number. What do I do in order to calculate the dynamic model?
The Euler-Lagrange equation.
The Euler-Lagrange equation. Let me make some room for it, which is telling me what? I get the derivative with time of the derivative of the Lagrangian with q dot. Q is the states, right? Q is phi left and phi right, and q dot is omega left, omega right, minus derivative with q equals to the inputs, right? How many generalized coordinates I have? 2, right? The states are 4. So basically here I derive once for phi left dot, or omega left, and phi left, and this will be the torque on the left wheel. And then I have the derivative with time of the Lagrangian with omega right minus phi right torque right. So I will get basically two equations, one for the left wheel and one for the right wheel of the torques. Can we do these derivations? Like quickly in our head. If I take this derivative with omega r, what do I? No, let's take the simplest first. Let's do the derivation with phi left and phi are. What's the derivation?
It looks like they don't depend at all.
So derivative will be 0, right? So these parts will be 0 for both. Great. What about the left side? Derivative with omega L.
The first one is going to be 0. The second one is going to be 2 omega L and the constant.
2 omega L and this constant. And
That is going to be 2 omega L and
2 omega R and a constant. Right? If I take the derivative of this with time, the constants don't change with time. Right? So what I will end up with is taking the derivative of this and the derivative of this. Correct? So this is accelerations. And similarly, I will end up with a 2 omega R square. I can even skip the square and put it in the constant, plus 2 omega L dot and some constant. Let's call this M11, M1, 2. Let's call this M12, M11, and this will be M21, M22. So in the end, what will I have? Equals to tau 1, tau R, tau L. I will have omega R dot omega L dot. It's basically accelerations times M11, M12, M21, M22 equals to torque right, torque left. Okay, so this is my equation of motion. This is acceleration, this is torque, this is some inertia. And the inertia matrix is basically fixed, nothing changes. Right, as long as the mass doesn't change over time or the inertias and so on, which typically don't, then I have a pretty straightforward dynamic model which I can use for simulation. It still has this form, right? But for our consideration, basically this part and this part are 0. And so this is the same form we saw for drone and for robot arm. Just the Coriolis and the gravity terms are 0. The gravity terms are 0 because we don't have any dependence on potential, right? The potential is constant, so gravity 0. And Coriolis is we don't have multiple links to move relative to each other. All right, pretty straightforward, I guess. Any questions? I'm not going into control because this is a very simple linear system. Can control it how we like. All right, good. So that's basically it for mobile robots. Again, we saw the concepts of kinematics, inverse forward, dynamic modeling, less on control. Any questions?